Hello. In the previous video to this, we looked at ellipses which were centered at the origin. In this situation, these ellipses are going to be centered away from the origin at some ordered pair, HK. So let's define the standard equations of an ellipse with a center at HK. So what I'm going to do is I'm just going to write these forms out first. We have x minus h quantity squared divided by some value a squared plus y minus k squared over a different value, which we will call b squared, equals 1. So all we're doing from our origin formula to our shifted formula is we're adding this minus h and minus k. Notice the minus h is always with x, and the minus k is with the y value. And then we have these two values which end up in the denominator between or beneath each term. A is going to be the larger number. So what we want to remember here is A is always going to be the bigger number. So A is bigger than B is bigger than 0. So we have to have a positive number. The larger number is under x. That means it's horizontal. So a vertical ellipse formula is going to look very, very similar. Merely the only difference is that we're going to have the larger number under y. So I'm going to write that. We've got x minus h quantity squared over b squared plus y minus k quantity squared over a squared. And so the reason we have to identify the orientation of the ellipse, not by which one comes first or which one comes second, but by the larger number in the denominator, is because this ellipse is organized with addition, and addition is commutative, which means it doesn't matter which one comes first. These are going to go, it'll both mean the same thing. So when we talk about hyperbolas have minuses in between them, and with a minus, order matters, right? 3 minus 2 versus 2 minus 3, those give you different numbers. So we can't determine horizontal or vertical based on the orientation of x and y. We have to look at where the larger number occurs. Again, for horizontal, the larger number is under x, and for vertical, the larger number is under y. In both of these situations, A represents the larger number, which is bigger than B. Both A and B are positive values. So now let's talk about finding the center vertices, the minor and major axis length, as well as the foci for these ellipses. All right, so in both of these ellipses, the center is at the ordered pair HK. And what we know is that the vertices, those are the furthest away from that center location. The vertices are determined by adding and subtracting your A value. So let's look at this. The vertices for a horizontal ellipse, we would add or subtract that A value from the X coordinate, or H. But with a vertically oriented ellipse, we would add or subtract that A value to the Y coordinate of the center, or K. Now the minor axis is going to be 2B units long, just like the major axis would be 2A units long. And then the foci are found using a value C. So again, the foci are going to lie on that major axis, and we'll have H plus or minus C, comma K, versus H, K, plus or minus C. And we already talked about how we know what that C value is. The C value is always found by saying C squared equals A squared minus B squared. It's very important for you to remember that's a minus. So when we start talking about hyperbolas a few videos from now, hyperbolas look very, very similar to this. The only difference is hyperbolas have minuses in between those two terms, and the C formula has a plus. And then because hyperbolas have minus, we can look at the orientation x minus y versus y minus x to determine if it's vertical or horizontal. All right, these are our two formulas. Let's sketch a picture of what a horizontal or a vertical major axis ellipse would look like. So over here on the left side of the screen, I'm going to plot my center at some ordered pair away from the origin, HK. Now keep in mind, this represents an ellipse with a horizontal major axis. So HK is right here in the center. Now, furthest out, we would have a distance away. So I'm subtracting A to get to this vertice on the left, and I would add A to get to the vertice on the right. Therefore, those ordered pairs are H plus A, comma K, and H minus A, comma K. The foci are going to be inside, also equidistant from the center. And then the minor axis, we're going to go B units up, whatever that B value is, and B units down. So we end up with an ellipse, which looks, and this is not the most beautiful, but it looks about like this. And I have kind of written those points in there so we can see what all of these different points are identified on the ellipse. Right, so what you want to notice is that C change, your foci, and the A change, your vertices, those are shifted to the left and right horizontally from the center to give us our horizontal ellipse. And that smaller number B, that's going to be my vertical shift. That's my minor axis. Again, let's look at this for a vertical ellipse. Here's my vertical ellipse. Again, I'm going to put my center somewhere off of the origin. Having that center, HK, located right there, I know I have some sort of vertical axis which travels through those points. So I'm going to shift up A units off that center and down A units off that center. So this should be symmetric, plus A, minus A, and we're adding those to the K value or the Y here on our center because our center is at HK and we're shifting vertically. That change is occurring in the Y. My foci are also on the major axis, somewhere between those vertices and the center, also equidistant. And then we'll have some B value. The B value goes to the left and the right. So sketching this, trying to make it look as ellipsy and symmetric as I can. It looks roughly like this. So you'll notice all of these points, my two vertices and my two foci, they are all vertical above and below my center. And I'm adding and subtracting. I'm adding A and C, subtracting A and C to the Y or the K value because it's a vertical change. And if I went to write these two B value, the minor axis vertices, that would be H. And since I shifted horizontally, that'd be H plus or minus B. So this would be H plus B, comma K. And over here we have H minus B, comma K. Right, so now that we have a good understanding of what these ellipses look like, and again, it's very similar to when they're centered at the origin, we've just, instead of having H and K be 0, 0, there's some other number in the coordinate plane. And again, now that we understand the patterning, the way this is going to lay out on the paper, let's do an example. Here, we want to identify the conic and its orientation, as well as state the attributes. Now, of course, you guys all know this is going to be an ellipse because we're in an ellipse video. But how do I know it's an ellipse and not a hyperbola and not a circle and not a parabola? Right? And we haven't talked about hyperbolas yet, but we do know what circles and parabolas look like. How do we know? Well, we look at this. We have two squared terms. If I have x squared and y squared, I know it is not a parabola. That means it's a circle, an ellipse, or a hyperbola. Another thing we look at are the signs. Since they both are positive, they're either both plus plus or both negative minus minus, since they're both the same sign, we know this is not a hyperbola. That means it's either a circle or an ellipse. And since my coefficients are different, we know it is not a circle. That means we know we are dealing with an ellipse. And we need it in standard form before we can determine the orientation. So for our orientation, we know we'll have some x squared, some y squared, and there will be a number under each. Whichever x or y has the larger number, that will let us know how to determine the orientation. So again, we really just wanted to focus on right here determining what we are looking at. And that's going to help us, again, as we move forward and we get into Calc 2 and Calc 3, where we really start dealing with different types of shapes in space. So as we look to put this into standard form, I group my x terms, I group my y terms. I'm going to complete the square twice to figure out what term I'm going to add to both sides of the equation. Again, we're doing that twice. As we look to complete the square, one thing we do is we always make sure we have a coefficient of 1. So for the x terms, I need to factor out a GCF of 4. And that leaves me with x squared plus 6x plus some number. And essentially, I'm not factoring out a GCF here, but we have one of those. So I'll write it that way just so it looks consistent. We need to figure out what number we're going to add. So I identify my b. Here I have that b equals positive 6. We find that magic number by saying b divided by 2 squared, or 6 divided by 2 squared. 3 squared is 9. I'm going to add 9. Now, I'm not just adding 1 9, I'm adding 4 9s. So I'm actually going to add 36 over to the right side of the equation. Same patterning over here. B is negative 2. Negative 2 divided by 2 squared is negative 1 squared, or positive 1. I'm going to add 1 value to the right side. And what this looks like, I end up with 4 times x squared plus 6x plus 9 plus 1, y squared minus 2y plus 1 equals negative 21 plus 36 plus 1. Now, both of these in parentheses, both these trinomials, they should factor. This is going to be x plus 3 quantity squared, and the second one is going to be y minus 1 quantity squared. And so that value that goes into our binomial, which we square, is always the number before we squared it in our completing the square form. We're almost to standard form. We end up with 16 on the right side. As I know I've mentioned before, when you're working through these problems, you should get a nice perfect square number over here. If it's not a nice perfect square number, you probably made a mistake, and I would go back up here and look at one of your previous steps. So now that we have this equal to 16, remember our standard form is equal to 1. So I'm going to divide both of the terms on the left by 16. I have x plus 3 squared. And we have 4/16, or that leaves us with a 4 in the denominator, plus y minus 1 squared. 1/16, that doesn't reduce, and I'm left with 16 in the denominator, is equal to 1. Now we're almost in standard form. I personally like to write one extra step, but you should be able to tell at this point we are dealing with a vertical oriented ellipse. So that means my major axis is vertical, and I know that because the larger number is under y. Now, if you recall from our standard form, both these values in the denominator were a squared or b squared. And you can see that right here. So I like to just go one extra step and always write those as a value squared instead. And so now I have my vertical ellipse in standard form. So this is a vertical oriented, that's my orientation is vertical, ellipse. A circle is the only one that doesn't have an orientation because it's the same width and length in either direction, vertical or horizontally. So now we can identify A is 4, B is 2. My center, H and K, are coming directly out of the equation. Remember, the standard form has a minus in it, so that means my center, HK, is going to be -3, +1. And the last piece of information we need is our C value, which we can calculate. C squared equals A squared minus B squared. C squared equals 4 squared minus 2 squared. We end up with the square root of 12, or rather 2 root 3. I do want to point out a common error. I sometimes see students use, say, 16 and 4 for their A and B values, rather than the root of each of those, 2 and 4. All right, now that we have everything, we know we have a vertical ellipse, we know our orientation, our center, A, B, and C, let's go about graphing this and stating all of the attributes or characteristics of this ellipse. So again, we have an ellipse. The orientation is vertical, and we know the center is at -3, +1. The foci and the vertices, those are going to be traveling vertically up and down off the center. Remember, for the foci, we use plus or minus C. For the vertices, it will be plus or minus A. So these changes are going to be occurring off of the y value, or 1. So my two foci, -3, I've got 1 plus 2 root 3, and -3, 1 minus 2 root 3. That's the exact way that we want to write them. We don't need to turn that into a decimal. Of course, we might want to do that on our paper or our scratch work in order for us to plot this if we needed to draw it, say on a lab. But, I want to see the exact value. So my vertices, I'm going to do the same thing. I've got -3, and I'm going to add A, which is 4. 1 plus 4 gives me 5, as well as I'll have -3. 1 minus 4 gives us -3. The minor axis vertices, the minor axis is a horizontal, and we use B in order to determine that. So horizontal means a change in the X value. So my minor axis vertices will say -3 minus 2, I've got -5, 1, and -3 plus 2, I've got -1, 1. So I took that -3 and I added and subtracted 2 to it to get these two new ordered pairs. The axis length of the major axis, that's going to be 2a, or 2 times 4, which is 8. And the length of my minor axis is going to be 2 times b, or 2 times 2, which is 4. And I had that other graph in there, but I didn't like the way it looked, my graph paper. So I'm going to actually use this graph instead. So we're going to plot the center at -3, +1. Now my vertices are going to be A units, 4 units above and 4 units below. So moving up 4 units, I get a vertice at -3, +5. Moving down 4 units, I get a vertice at -3, -3. And my minor axis vertices, those are going to shift 2 units out to the left and 2 units out to the right. And then the 2√3 value, the square root of 12, that's approximately 3.5. It's 3.464. So that means I'm going to shift up 3.5 units and down 3.5 units. So I'm about half a unit above and below each of these vertices. And sketching my ellipse, let me try and make it look nice and round-ish, not pointed corners. We get something that looks like this. So here is our vertical ellipse. And of course, a horizontal ellipse would be very, very similar. We would just be changing where these A, B, and C values attach off of our center. Just recapping, in the video prior to this, we talked about an ellipse which was centered at the origin, and that H and K value was 0. So this is the same formula, we just expanded on that to shift it or translate this ellipse away from the center. As always, email me if you have any comments, questions, concerns. I am here to help. Good luck.